Jesus neural nets, and well, the floor is yours to tell about what you're going to tell us. So thank you.
Okay. Thank you. Let's see how it goes. Anyway, so before we move on, a little bit of background. First, I will invite you to visit my webpage. Just put my name on Google and the first hit. As far as I can tell, there is only like around 12 Fernandez Villaverde in the world. And none of them have done much. If you bump into someone who's a novelist, that's my brother, so that's not me. And if another one is an architect that builds buildings nearly as ugly as this one, that's my other brother. So the third one should be me, who is the economist. Anyway, if you click on teaching, you will see that I have a bunch of courses and I post everything online. And perhaps the course that you can be interested in the most is machine learning for macroeconomists, who is this one. And forget about macroeconomics, it's really a course on machine learning, just that some of the examples are on macro, and you can see over there a lot of material. So you will see, for instance, how I have a brief introduction to the ideas of machine learning, how I have some slides on coding, how I have some slides on deep learning, optimization, if you want to learn about Adam, another of the optimizers, how to apply this to economic models. I have some advanced topics dealing with issues I will mention today. Then today I'm going to focus a lot on symmetry in dynamic programming, and hopefully the slides that I have shared with you and the slides over here are either the same or an epsilon variation. Then you will see some material I have also on transversality and stationarity with deep learning, which was going to be one of the papers presented in the conference, but then my co-author cannot make it. Then I also have some stuff on reinforcement learning. You will see there is some machine learning for data analysis. I also have some material on text analysis, and I have a new set of lecture notes on large language models. And in fact, if you are interested on large language models, if you click here on research, you will see that just last week, well, 2 weeks ago already, I gave a talk for the Macrofinance Society on large language models. And what I think is interesting about that is that I'm going to talk in that talk, and you have the video over there. I discuss a lot the concept of embedding, which is, I think, my opinion, the right way to think a lot about what machine learning is doing these days, and you may enjoy it. Okay? And I think it's, it's a nice lecture. But without further ado of what is going over there, let me get into the presentation itself. And what I'm going to do is I'm supposed to have 2 lectures, one on symmetry in dynamic programming and machine learning, one in solving models with heterogeneous agents. I'm not going to constrain myself to be like 80 minutes and 80 minutes. Let's just go on, and we will make a stop anyway in the middle. But if I need to use like 10 more minutes of the next presentation, that's okay. The good thing about dealing with models with heterogeneous agents is that already this morning we saw deep ham, so you already have a brief idea of how these things can go. Okay, so let me start talking about how to exploit symmetry in high-dimensional dynamic programming, and more importantly about the role of symmetry in machine learning. And of course, let me point out that this is with a lot of co-authors, with Magdi Ebrahim Kahu, who is just moving to Bowdoin College at Maine, with Jesse Perla, which is in some place in British Columbia, and more importantly, with Arnab, who is around there, so he will be the one answering all the relevant questions that my limited knowledge of mathematics will preclude me from addressing in more constraint. And I want to make this like full presentation. I imagine it's Control L or something like that.
Upper right. Arrows.
Down, over here. I see. Okay, yeah. It should be a crime against humanity to use a Windows machine, but it's okay. Okay. So let me tell you a little bit why this is interesting, and let me tell you a little bit why this idea may teach you a couple of things about machine learning that go beyond how we are going to apply it in this paper. So you take a standard course in macro, and you are going to see 2 big classes of models. So perhaps the first semester, you are going to see models with a representative agent. So think about the standard real business cycle model, think about the standard Neo-Keynesian model. Yeah, you may even see 2 agent models. Okay, so for instance, if you think about models where there is some type of financial frictions, sometimes you have a bank and a borrower, sometimes you have a high aversion person and a low aversion person. Okay, so we use these models and we have run a lot with models with representative agents. On the other hand, maybe in the second semester in the first year sequence, you learn models with heterogeneous agents where heterogeneity is a continuum. So what you have, for instance, like in the very basic Russell-Smith model that we already discussed this morning, is we have a continuum of households, and every household is subject to some idiosyncratic risk, and that generates a non-trivial distribution. And we have used these models as well to learn a lot about issues like business cycles, asset pricing, optimal policy, etc. Well, should not be a surprise that between 1 and infinity, there is a lot in the middle. Okay? And in particular, there is a lot of models where we want to have a finite but relatively large number of economic agents. So let me give you a few examples. Think about the models where we are going to have many locations. So I'm going to give you concrete details. I'm appointed the president of the European Central Bank. Don't worry, ain't going to happen. But imagine that I was the president of the European Central Bank. I want to have a model of the Eurozone. And something we know about the Eurozone is that the way in which monetary policy affects different countries is very different. For instance, there are countries with a lot of the mortgages are fixed rates and countries where most of the mortgages are variable rates. So I want to have a model that has that granularity, that incorporates locations with some properties of the mortgage market and some other locations with other properties. Let me think also about models where you have perhaps different regions that are subject to many different shocks. One little thing that a lot of people do not appreciate is why the US economy didn't do so well between 2013 and 2017. Well, turns out to be the case that if during those years you were living either on the East Coast or on the West Coast, the economy was actually doing really well. It was booming. You will go through shops in Manhattan and all of them will be filled with advertisements, help wanted. And yet the US GDP was not doing that great. And the reason was because the US is more than the West Coast and the East Coast. It's also, for instance, Texas and a whole column that goes from Texas to North Dakota. Those states are actually, right now, the #1 producer of oil in the world. Okay? If Texas was an independent country, it would be the 3rd largest producer of oil in the world, only behind Russia and Saudi Arabia. 2013, 2017 were years where the oil price was not very high. So the economy of Texas didn't do so well. So you're basically having a model where on one hand, the East Coast is doing very well, and on the other hand, Texas, Oklahoma, and the Dakotas are not doing that well. So if you are from the position of Washington trying to decide what is the optimal monetary policy for the US, you need to be aware that you have these different regions. Let me give you another example. Models where you are going to take seriously the fact that you have different metropolitan areas, and that metropolitan areas can be very important in the weight of a country. The standard case, of course, will be in France with Paris or in the United Kingdom with London. Okay, so if I were working for the Bank of England, the fact is that London is a very different animal than Yorkshire, and you may want to incorporate this idea. There is a second type of models where we also want to have this N type of agents. For instance, models with overlapping generations. And now, of course, within each generation, you may want to have a continuum, but you want to have a finite number of generations and take seriously the fact that you have those generations. Simon this morning used one of those models of overlapping generations. You went very quickly over the slides as a motivation for deep neural nets. Okay, and those are very important if we want to think about issues like social security reform or the distributional effects of climate change mitigation policies, etc. We also have models of industry dynamics with many firms. So imagine that I want to write a model, and this goes well beyond macro into industrial organization, where I'm going to have 6 companies, 6 car manufacturing companies competing with each other. And I want to keep track of how that industry evolves over time. And of course, models with networks. And that's actually a paper I'm just writing right now with Hikaru Saigyo and Tristan Matthews, where we are going to take seriously the fact that you have a network of production and economy with inputs and outputs, and you may want to have endogenous exit and endogenous entry within that network instead of taking the network schema. Okay. I think this class of models is very interesting. I'm not claiming it's the only class of models that I'm interested. In the conference on Thursday, I'm going to show you a very old plain vanilla model with heterogeneous agents on a continuum, but there are many questions I'm interested in that require to have a finite but large number of ends. Okay. And the reason why I think over the next 10 years or so, this is going to become more important is because we have a lot of microdata, and in the microdata, we don't have a continuum. There is no such a thing as a continuum of US household or European households. You have in the US, like what, 340 million people and change, so around 180 million households. Okay, and you may want to map microdata, which is finite, into your aggregate model. Okay. Now, let's imagine that we are going to think about these models with a finite number of agents, and in this model, to make things interesting, you have both idiosyncratic shock at the level of the households or the different agents, if they are countries or regions, and we have also aggregate shocks. So you cannot really compute something like a steady state, some type of ergodic distribution. Okay. The problem over there is that agents in the model need to keep track of their own states and the states of everyone else. Okay? So let me give you a very simple example. The standard model of international real business cycle models is Backus, Kehoe, and Kidland, 1992. And basically what you have over there in the original paper is only two countries, and these two countries are trading with each other, and they are subject to shocks. And what is going to happen is that every country is going to be characterized by 7 states. It's going to be their productivity shock, and some demand shock, and some level of capital, and so on and so forth. Okay? Maybe you can get away with only 5 states, maybe you can get away with only 4 states, but you have 7 states per location. In the original model, you have 2 states, or 2 locations, excuse me, so it's not very difficult to keep track of what is going on. You basically have my 7 states plus the 7 states of the other location. And, you know, they do a first order approximation, so it's not that difficult. But imagine I want to say, okay, let me think about the Backus, Kidland, Kehoe problem and apply to the United States, so I can really have a model to think about how different regional shocks affect different locations in the US economy. I'm going to have 50 states, 50 locations. Okay? And then what you need to keep track is of the states of each location and the states of every other location. And that gives you 350 state variables. So how do you solve a model with 350 state variables? And if you don't care about my example of the US, maybe you care about the example of the Eurozone. There are like, what, 27 member countries of the Eurozone? Well, we're not in the Eurozone, but you know, there are 27 members of the Eurozone, and imagine that you want to keep track of 3 or 4 states per member, then suddenly you have 108 states. Okay, so how do you solve a model with dozens and dozens of states? Well, something you can do is you can say, okay, fine, I do a perturbation. And we know that you can scale perturbations up to thousands of state variables. It's not a big deal. The problem is that many times the questions that we are interested are inherently nonlinear. So for instance, the paper I will present on Thursday is about the zero lower bound. And so you're the European Central Bank, and when you're trying to decide the monetary policy for the Eurozone, you are hitting the zero lower bound. That changes the way you want to think about the world. And that will be the point of my paper. Well, if that's the case, then a perturbation will not really solve your problem. And a zero lower bound is nothing more but a particular example of an occasionally binding constraint. Or maybe it's because your model presents some type of non-ergodic behavior. What type of non-ergodic behavior I'm thinking about? Well, imagine that your model doesn't have a steady state. You may have a model where there is growth, there is some type of endogenous growth, and you don't have a simple balanced growth path that you can somehow rewrite your model in a stationary form. Okay? You know, just pick any of the papers by Philippe Aguillon and his co-authors. There are plenty of examples of those type of models. Or models where you have large transitional dynamics. Okay, so one of the main problems that the profession has is that if you want to publish papers in the top 5, most of the editors are going to be from the US or working in the US, and they are going to think about the US as the standard. You know, has been growing roughly at a balanced growth path since 1865. But that's a completely silly way to think about the world for pretty much everywhere else. So let's imagine that I'm thinking about China, and I want to write a model about China. Well, China, I recently wrote a model with Wen Yao about that, has gone through a huge transitional dynamics since the start of the reforms in 1979. And that means that instead of being through a balanced growth path, you are going through a convergence towards some type of balanced growth path. And that induces a dynamic that is very different from what you can capture by a simple perturbation. Now, I know that there are ways, and I have worked on those, where you sit down and you may be able to find some representation of the model that has a perturbation solution approximation that is accurate enough, but in general, that's not going to be possible. Okay, so perturbation, not really the solution for many of the problems we care about. What about the sparse grids, like the ones that Simon has worked with Broad? Well, I guess you will agree with me that you can push this to 20, 30, maybe 50, but if you want to go more than 50, ain't going to happen. Okay, so sparse grids are great. I have written papers with the sparse grids, and every year I teach the paper of Felix with Dirk to generations after generations of gravity students, and I always show that three-dimensional graph that you guys have with blue dots. And every year, students look at me saying, oh my God, what did I do to deserve this punishment? But at the end of the day, if you really want to go to 300 state variables, that's going to be good. The possibility is, what about something that looks like Russell-Smith? Okay, wait for it. We are going to come back to that. Very good. Okay. So this, at the end of the day, is nothing more than yet another incarnation of the course of dimensionality, which we have been discussing already over the last 3 days. And I will invite you to go to the original monograph by Richard Bellman on dynamic programming, where he introduces the notion of the course of dimensionality. It's in page 9 of the introduction. By the way, Richard Bellman is someone who should put all us up to shame. If you go to his wiki page, you will realize that he wrote his dissertation in 3 months. Okay. So the first point that Richard Bellman points out is that the cardinality of the state space is enormous. So think about a very simple problem where we have 266 state variables, and we are only going to have 2 grid points per state variable. Okay. That maybe, I don't know, it's just a village, and we are doing some type of risk sharing between the 266 of us. Think about this type of, these risk sharing models of Townsend and all these guys were trying to think about like informal way of insurance in villages in development economy. So let's imagine that we are dealing with a village with 266 households. Their idiosyncratic shock is just high or low productivity of their crop. And we are only going to have 2 polynomials per state, a level and a slope. Well, it turns out to be the case that that simple model has more coefficients that we need to solve for than the Eddington number, which is the number of protons in the universe. Okay, so, again, that's not going to happen. There is a second aspect of the course of dimensionality that is less appreciated, but that was at the very core of what Felix was telling you before, which is it is very difficult to evaluate highly dimensional conditional expectations. Okay? Expectations are the nemesis of every economist. Think about when you took calculus for the first time. You learn to do derivatives, but I don't know, like what, in an afternoon? Fine, derivative of x is 1, derivative of sine is cosine, and that's it, pretty much. That's everything you need to know. Okay, if you have, a little bit of half a brain, in 2 hours you know how to take derivatives. However, you continue with your calculus class, and you're going to spend 6 months learning to do integrals. Okay, and if you have kind of a little bit of a nasty teacher, as I had in high school, you will need to learn to do like all these derivatives with geometric transformation, with the change of variables, blah, 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 blah. Why? Because integrals are hard objects. And that shows up when we are trying to evaluate expectation, which is nothing more than a conditional expectation, because computing integrals is an exponentially hard function of their dimensions. It means that computing an integral grows exponentially in the number of dimensions. Okay? When I teach my graduate course on computation, I have this homework where I ask the students to integrate a very standard function in 1 dimension, in 2 dimensions, 3 dimensions, and you go for taking like 5 seconds using a quadrature rule to taking 5 minutes. And why are these expectations important? Because they show up pretty much in every dynamic programming problem, either directly in the value function, as we saw yesterday when we were revisiting Rust 1987, or indirectly in the Euler equation in the optimality condition. Marian utility today is equal to some type of expected Marian utility tomorrow. So it's very difficult to get around from expectations, either if you're approaching this as a as a dynamic programming problem, or you're approaching this as a policy function problem. Okay. So what can we do about this? And how can machine learning help? And this is going to be very interesting because it's going to teach us a lot of things, not only about dynamic programming, but as I promised, about the reasons why machine learning works. Symmetry. Symmetry is one, if not the most powerful idea in math and in physics. This is, of course, Hermann Weyl, one of the greatest scientists and physicists of the 20th century. And when he retired from the Institute of Advanced Studies at Princeton, yesterday, I think it was John Rust that showed a photograph of Johnny von Neumann when he was at the Institute. By the way, the Institute of Advanced Studies is at Princeton, it's not of Princeton. A lot of people kind of don't get it, but it's okay. And when he retired from the Institute, he gave a series of lectures that he published as Symmetry. It's published in Princeton University Press. It's a beautiful book, which I invite anyone who's interested on some of these issues to read. Even being nearly 80 years old, it's still enormously insightful. And Weyl says symmetry, as wide or as narrow as you may define its meaning, is one idea by which men, back then people would say men and not persons or humans, thought through the ages has tried to comprehend and create order, beauty, and perfection. Okay. Symmetry is a vast subject, significant in art and nature. And when I get to this point, I always like to show this. So this is, of course, part of the score of the Goldberg variations. And you should remember that no day is complete if you have not listened to Johann Sebastian Bach, at least for 5 minutes. And the Goldberg variations is one of the best pieces in the canon of Western classical music because it has an absolute wonderful set of symmetries built into it. And Bach thought about this perfectly. So the Goldberg variations, there are 30 of them. The first 15 are symmetric with the next 15. And then you have another symmetry between the first 10, the second 10, and the last 10. And then you have symmetries in all the thirds. So the third is symmetric with the 6 with the 9 with the 12, and so on. But even within each variation, you have symmetry. And this is the beginning, the first half of the 26th variation. You can see there is exactly the symmetric form of the second half starting on the verse 17. And that's the reason when you listen to the Goldberg variations, you realize it's something it takes a lifetime of understanding. Okay? So symmetry is something that appears constantly in nature and in art. Philip Anderson, another very famous physicist who got the Nobel Prize a few years later, went as far as saying it's only slightly overstating the case to say that physics is the study of symmetry. Okay. So what do we mean by all of that? Okay. Symmetry means that there is going to be an underlying structure within our problem that we are going to be able to take advantage of. And that once we exploit that structure, everything is going to be much simpler. Okay. We actually use symmetry all the time in economics. We just don't think very carefully about it. So think about the Walrasian auctioneer. What does the Walrasian auctioneer do? The Walrasian auctioneer collects excess demands from him excess demand from him, excess demand from him, excess demand from him, aggregates all of them and has an aggregate excess demand, and then searches through Tatonement to the price that clears the market. The amazing thing about general equilibrium is that his name doesn't matter. He's symmetric with him. If I take his excess demand function and I swap with his excess demand function, the aggregate demand function of the economy is absolutely the same. So at the very core of general equilibrium, we have a symmetry built in. We only care about the excess demand of each individual. We do not care about the level of each individual. And that's actually something that Paul Samuelson understood in many papers, and I just cited in there 1990. Karel Mertens and Jad have also made a similar result. I'm not going to go over all the literature review, but if you look through mathematical economics, game theory, general equilibrium, there is a lot of places where symmetry appears, even if we don't call it symmetry. In fact, it also appears all the time in industrial organization. They have a slightly different name for that over there, but I will come back to that in just 1 second. Okay? Why is symmetry important? Because symmetry may not be obvious at first sight. Symmetry may appear in some transformation of the underlying space in which we are working. What do I mean by that? Think about the start of functional approximation theory, all the way to Chebyshev and these guys and Weierstrass and all these people in the 19th century. Basically, for 150 years, the goal of functional approximation theory was to try to come up with better and better basis functions to approximate the problem that we were interested in. Okay, and then you will pick books that will say polynomials, and you will read, you have this Laplace polynomial, and you will have the Chebyshev polynomial, or you will have this radial function, and you will try to think a little bit about which approximation was better, given the particular properties of your problem. What symmetry underlines, and I'm going to come back and explain it in a little bit more detail in just 5 seconds, so give me your benefit of the doubt for a second, is that's not what you want to do. What you want to do is transform the geometric space in which you are doing your approximation to a geometric space that is convenient. And then pretty much with any base function, you are going to get it right. So that's really a complete change in the way you want to think about the world. And I'm going to use a prop. And some of you may have seen me doing this prop before, so I apologize for the repetition, but some of you may have not. Imagine that I want to approximate this ball of paper. And to make this more fun, instead of being a 3-dimensional object, imagine that this is a 200-dimensional object. So this will be an extremely complex ball to approximate. Why? It's irregular. It has all these ridges, peaks, valleys, etc. Good luck trying to approximate this using Chebyshev polynomials. It's just not going to happen. Okay? Now, let's imagine that I can operate over this space, and remember, this ball belongs to a 3-dimensional cube, so it's holding in the middle of this 3-dimensional cube, and what I'm going to do is I'm going to twist the cube in different ways, okay? And I'm going to do something very simple. I'm going to do translations and rotations, the 2 basic operations in any geometry, okay? Turns out to be the case that translations and rotations are exactly what we do with a neural network. Because a neural network takes an input, rotates it with an activation function, and then translates it with the weights. Okay, and they're also going to be, this in itself is going to be like a linear combination. Okay? In fact, if we were going to pick a better name for machine learning, it could be chain geometric transformations. Because it's much closer to the truth. Felix was absolutely right when he said, what the heck does mean machine learning? There is no machine learning over here. And really, there is nothing inherent about being digital. In French, you say aprendizaje automatique, no? In Spanish, we say aprendizaje automático. It makes much more sense. Okay? Well, let's think about this ball in this three-dimensional space. And let's do translation. What is a translation? A translation just means moving like this. What is a rotation? A rotation, as the name indicates, is to rotate this. And we are going to keep doing this. And we are going to keep doing this. Remember, we are just changing the underlying state space. And if I do a sufficient number of those translations and rotations, no matter how complicated the ball is, what I have at the end of the day is an Euclidean linear space, which I can approximate in a trivial way. And by the way, some of you were asking about the intuition behind breaking the course of dimensionality of the original Barron theorem. This is really the true intuition and not something complicated about spectral densities. You have basically redefined the space in which you are doing your approximation to a space that is convenient. That's all you need to understand about machine learning. In fact, I will strongly encourage you to go, and now I'm going to go back to this thing. Oops, I can't figure it out how to do it. Okay, this is a fantastic book, and the great thing about it is that it's free online. Geometric deep learning, grids, groups, graphs, geodesics, and gauges. And that goes in detail over all these ideas I'm showing you. It's an absolutely fantastic book. It will blow out your mind. I mean, when I read it, I couldn't put it down. I was like, wow, this is completely and radically changing my view about what deep learning is. Because again, what deep learning is nothing more that we go from a bad space into a good space. Okay? And you have already done that thousands of times in your profession as an economist. So let me show you. You go to intermediate micro or intermediate macro. You are introduced to our good old friend, the Cobb-Douglas production function. And very soon you realize that dealing with the Cobb-Douglas production function, as easy as parsimonious as it looks like, is surprisingly difficult. You start doing algebra, and I have done enough algebra in my life with the Cobb-Douglas production function to realize that, sometimes there is just one coefficient that disappears and it doesn't show up where it's supposed to show up. And then you say, what if instead of expressing this in the quote-unquote natural space, which is the levels of capital and the levels of labor, we express this in logs? Then what you have is that the log of y is alpha, the log of k, plus 1 minus alpha, the log of L, which is a nice linear function where, as I was saying before, even most undergraduates in sociology are not going to make mistakes. The problem is that we transform the Cobb-Douglas production function into a linear structure using domain knowledge. What do I mean by domain knowledge? We understand the geometry of this function. We know enough about the properties of the logs that we knew that we should take the log of k and the log of L. The problem is that in general, when I'm doing an approximation in abstract, I don't know that. Imagine that I'm trying to approximate a very complex problem in thousands of dimensions. How in the world I'm going to do that? That's what the neural network is going to do for you. The neural network is going to take the inputs, it's going to translate them, rotate them, and get you back into something that is linear, or as close as linear as possible. Okay? That's why this thing works. Now, once you start thinking about this, you realize that the doors to do pretty much everything are open. Because it means that any piece of information can be translated and rotated in the right way until it belongs to some type of simple vector space. And that's known as embedding. Okay? So embedding basically is some way in which we are going to take a set of objects and transform them into vectors. These objects can be the states in our economic model, but they can be photographs, they can be words, they can be three-dimensional objects, they can be videos, they can be conversations on Twitter. Anything out there can be embedded through the right architecture into vectors. Why is this so important? Because once I have vectors, I can apply linear algebra, and I can manipulate those vectors, and then just unembed them into the original object. So let me give you a very simple example of what I have in mind, and how we are going to apply that into dynamic programming. Just one second. Basically, what GPT does is it takes words. So let's pick a word, France. And it's going to embed that word into a vector. 0.3, 0.2, 0.7. Okay. In the case of GPT, it's going to be a 12,228 dimensional vector. And then we are going to take another word, Paris. And it's going to embed it into another vector. And then we are going to take another word, Spain, and it's going to have another embedding. So I'm going to be able to define the following operation: sum France plus Paris, which is just sum into vectors, subtract Spain, which is that vector. And you're going to get a fourth vector. And you know what that vector is going to be if you have trained the model properly? It's going to be Madrid. That's why ChatGPT can forecast the next token in your conversation. Because it has basically taken all the possible words, you have trained the model into some embeddings, and this is the result. Yes.
What was the operations that you did to get Madrid?
I did plus, minus. Okay, remember, this is the country, this is the capital. So I see the country plus a capital minus another country should give me the capital of the next country. But the amazing thing is I'm never telling the computer to reason that this is a country and this is the capital of the country. It's just by embedding in a sufficiently highly dimensional vector that I'm capturing all the information that I need. Okay? This is in opposition to the traditional artificial intelligence. Okay. So artificial intelligence as a project starts with a very famous summer workshop at Dartmouth, which is fortunately for them a little bit milder than here. Well, it was in the 1950s, so also there was no global warming. But bunch of people get in Dartmouth, and they basically say, okay, we are going to figure it out, artificial intelligence, in between 3 to 6 months. Turned out to be the case, it was not so successful, but basically the project at the time was to tell the computer rules of reason. It was to somehow code, think that this is a country, think that this is a capital, and then infer that if I'm put in another country, the answer I want is another capital. That turned out to be the case, that it was too complicated. There are too many rules, too many situations to be able to make these expert systems work in practice. The point is, if you have the right embedding model, you don't need to worry about it, because everything is going to be in this highly dimensional space, and you are going to be able to define all these operations. And behind all this, what you have is a concept of symmetry. That at the end of the day, different objects, even if they look very different and very complicated, they are just vectors in some particular space, and that particular space is actually going to be surprisingly low dimensional. Well, if you want to call 12,000 words, 12,000 dimensions low dimensions, but the point is, that's why ChatGPT is so impressive. It can really, you can put and say, write an essay on economics on the style of Shakespeare, and it actually produces something that more or less makes sense. Okay? Okay. So that's what we are going to try to do in this paper. We are going to try to think about ways in which we can represent the geometry of models with many agents taking advantage of their symmetry. Now, I'm going to be skipping material that you can find on my webpage. You go to my webpage on the course, you will see a block 6 where I discussed something called the Erlangen program. Okay? The Erlangen program was proposed by Felix Klein. So Felix Klein became professor of mathematics in Erlangen when he was only 23 years old. And back then, I don't know if they still ask this to the German professors, when you became a professor, you were supposed to give a talk outlining your research agenda. And what Klein is trying to do is trying to say, look, remember, this is like the late, well, second third of the 19th century. At that moment, geometry was in a state of a mess. Okay? So all of you, when you were in high school or maybe middle school, you learn about Euclidean geometry. Okay? Like the very basic facts of geometry, parallel lines, perpendicular lines, all that stuff. Then, in the early 19th century, people start developing new geometries. They start coming up with the projective geometry. They start coming with the affine geometry, and later on with all the general Riemann geometry and all the other classes of neo-Euclidean geometries. And what people get very confused is, well, I have like this theorem for this type of geometry and this other theorem for this other type of geometry, but there must be something that links them together. So the Erlangen program is the idea that you can actually define and prove theorems for a general class of geometries instead of worrying about that particular geometry. And the Erlangen program was very successful, and by the mid-20th century, we had a geometric approach that didn't depend on a particular geometry. Okay? And that, by the way, gave birth to category theory. I don't know if any of you took some category theory as an undergrad. Okay. Why is this so important to what I'm trying to say? You can think about all the architectures of all possible neural networks as a particular example of this much more general abstract neural network. We can prove theorems about those neural networks in abstract, and don't worry about implementation details, because the theorems are going to hold. Of course, we need to worry about some of the details when we actually do the coding, but when you think about this from the theoretical perspective and the way you want to approach much deep learning as a way to think about the world, what the Erlangen program is telling you is, at the end of the day, if everything is about finding the right geometry, think about this in the abstract way. Don't think about this in concrete ways. So is this going to be the architecture that Simon presented this morning, or is going to be this the architecture that we saw with DeepHam? Doesn't matter. At the very fundamental level, as my former colleague and the former colleague of Felix used to say, Randy Wright, details. So just really details. It's not the essence of what we are doing. Okay? In particular, when you link with the idea of the double descent phenomenon, which at the end of the day says, if your architecture is sufficiently overparameterized, the details of it do not really matter. And then also, you want to check my block 13, which is the one I briefly discussed in the video that I showed you before about foundation models. Okay? So in some sense, I was talking with some of you during one of the breaks this morning, and I made the joke that large language models are so 2022. Okay, it's just yesterday's news. Okay, so if you are trying to catch up with large language models, sorry, that's not really what the cool kids are thinking about anymore. These days, what we are thinking is about foundation models. And the idea of foundation models is that we can have maybe an embedding that is sufficiently general that can take anything into vectors, as I was saying before. And the reason why we really believe we can have these foundation models who are going to get us much closer to some form of general artificial intelligence or sufficiently general artificial intelligence is because we have really come to appreciate how powerful is the transformer architecture. And by the way, transformer is the T in GPT. Okay, GPT means generative because you generate new content. P is for pre-train because the neural network has been pre-trained, and the T is for transformer. So what really, really matters over here is the transformer. And actually, you can show that a lot of the neural networks that Simon and I have been doing in different papers are just particular forms of a transformer, which is this much more general way to think about the world. Okay. Okay, I know this discussion has been a little bit abstract. It has involved a lot of different things. We have jumped from geometry to transformers and to generative AI, but questions before we get into details.
So when you talk about embedding, I think you already talk about finding the right sort of space.
Exactly, to represent any piece of information.
So what do you think about when we talk about foundation models or large language models, how do you view the sort of whether there's any symmetry there? Or it's just it's more like a sequence model. So
okay.
There's order here.
Yes. So the fundamental symmetry embedded in GPT, for instance, I invite you. So it's really interesting. If any of you is interested, read the original paper by Baswani et al. 2017. That's the paper that proposed it's called Attention is all you need. Okay. And in that paper, they actually take advantage of the symmetry in the language. Okay, and they take advantage that English is a language that has a very particular structure, and in particular that the words in English tend to have an ordering that you should exploit. Okay, and that. Okay, so let me give you a concrete example of the symmetry they try to take advantage. I know this is taking us a little bit from dynamic programming, but at the end of the day, you will realize it's all the same. No, because it's really all the same. That's the point. That's the absolutely unreasonable effectiveness of math. Everything is the same.
It's a feature of human society.
Yeah. Okay, so this is a famous sentence by a very famous English linguistic. I sit in the bank at the bank office by the river bank. Why is this a very interesting sentence? Because bank over here means a bench. Okay? Bank over here means a financial institution. And bank over here means the side of the river. And the challenge, actually the sentence can go longer. In my lecture on large language models, I say at the river bank, where you bank, referring to the use of bank as a verb. Okay? Of course, this actually makes sense, because if you know a little bit of monetary history, the reason we call banks banks is because Italian bankers seated on benches in the Middle Ages where you went and do businesses with them. But nonetheless, that historical origin is irrelevant. The problem is, how do we make the computer understand that bank over here is different from bank over here and bank over here? And we do not want to have three different embeddings. We want bank to have only one particular embedding. And what we are going to take advantage is of the fact that the word bank follows the word sit. And that at the bank, this follows this, and that bank over here follows river. Okay, and that's the symmetry. We basically, the way ChatGPT, because ChatGPT is just the chatbot on top of it, but GPT basically always looks at the words right before with a mechanism called attention that tells you what type of word that is. Okay, and that's the symmetry. The symmetry is that the informational content in English always goes forward, never goes backward. Now, you need to work a little bit on it because, yes, you are going to tell me that there are some exceptions in English. Okay? But that's why if you are going to write a language model in Latin, it will be very different. So I don't know how many of you took Latin in high school, but Latin is a language where you can order the words in any way you want, because they have declensions, like in German. Okay? In English, I say I sit in the bank, the information is in. Okay? In Latin, it will be in the grammatical ending of the word. Well, the only thing then I need to do is rewrite the symmetry in looking for grammatical endings. Okay? So there is a symmetry in both cases. In English, the information runs in this direction. English is an analytic language, while in Latin, the information comes from the ending, is a synthetic language. Okay? But at the end of the day, everything is about thinking the right geometry. And if you go to the paper by Vaswani, they have a very nice metrics where they make this point.
Yeah, I feel here symmetry is sort of like an invariance.
Yes, because symmetry and invariance are very, very closely related. Okay? I know this is a little bit at an abstract level, but we are going to start doing some real math in a second, and that will be much simpler to follow. Anyone online? They just gave up.
Online? Yeah. Can I?
Oh, sorry.
You were talking about Latin.
Yeah.
Embedding would be different in Latin.
Yes. That's why you cannot use, that's why you can just not take ChatGPT from English and retrain it into Latin, or the same thing with Chinese.
There's ChatGPT in Latin.
It's actually, it will be rather straightforward to code. Okay, it's just that there is not going to be a lot of money in it. But this case much more complicated, for instance, if you want to write a GPT or the equivalent of a GPT in Chinese, because Chinese is really a very different grammatical structure.
Embedding would be different.
Yeah.
I mean that in Latin, the embedding would be different than it would be in English. Depending what the role of the word is.
Yes, exactly. That's what I mean. The embedding model will be different.
Yeah.
Okay, that's exactly what I'm saying. You will need to take account of the fact that in Latin, the ordering of the words is not informational. What is informational is the inflection of the word. Okay? Even in English, you still need to do a little bit of that. We actually have a little bit of a residual of declination in English. Declination in English. Because we say I, my, me. That's just the residual of the old Germanic declination in English. Okay, it's just that in Latin they still keep rosa, 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 rosa. Okay, so you need to write a different language, you need a different embedding model in the same way that if you are going to transform photographs, you will need a different embedding model. The promise of foundation models is that if you sufficiently over-parameterize these things and you have sufficient number of parameters, the embedding model is going to figure it out. These words are in Latin, these words or this text is in English, and figure it out that the symmetry it wants to impose will be different. But we are not quite there yet, but that's the promise of the foundation models. Whether or not they will be able to deliver on that promise, I don't know, but that's what people are after. Yes.
So the embedding model, can I think of it as the first layers in the neural network?
Yeah.
And each layer would rotate and translate until it becomes like nicely linear?
And nice little vectors. Well, I don't want to say encoder, because that's actually something that is a little bit misleading about Vaswani et al. Vaswani et al. Claims you need both an encoder and a decoder. Actually, you only need one of the two. You can write things with only a decoder, and GPT doesn't have a decoder, it only has an encoder. Sorry, if you don't know what this is about, don't worry about that. Yes. But yes, basically what you are doing is you are doing a lot of neural network transformations, and you go from a photograph of your cat into a vector.
And the vector would be somehow the loadings on the last layer?
Yes. That then you are going to do things, you are going to then, what you will do, in the case of a language model, is that you will pass it to another layer, that is the layer that will forecast what is the next word that you want to have. Okay, so embedding, basically, the idea of embedding is transform any type of information that you care about into vectors. And now they are vectors, you do with them whatever you feel like.
But it's a smart, like, it's a smart.
Yes, exactly.
Part of already the
Yes.
reasoning is
It's how you do the embedding model. Okay, and then the embedding model, you can do it with some type of encoding, but you don't need to do that. You can do it the way GPT does it with something called multi-head attention. But I don't want to bore you. In the video, I explain what multi-head attention is. Yes.
Yeah, I don't want to start the conversation, but okay. From any input, whether it is images, text, you transform it to get an embedding, a word embedding or whatever. And then your goal is maybe to estimate something or predict.
It depends for what, no, but that will be the next level. That will be, as he was asking, the second part of your neural network, whatever your objective function, coming back to Simon this morning, whatever objective function you have. Sometimes it can be prediction, sometimes can be whatever.
What I'm curious about is, okay, you're parting from an input that has a particular structure that has valuable information that you use to establish inference. Because it's not the same a confidence interval for what the next word will be, such as to what will the next image will be. Are there any established results on those inferences?
No, these guys are engineers. Period. Okay, I make this joke before, you may have heard it. This is my father. My father is an aerospace engineer. Okay, my father doesn't worry about any of those things. And I was explaining that the other day. We don't know what airplanes fly. Okay, go to the internet and put why do airplanes fly? And the answer is we do not know. We don't have a mathematical theory of why they fly. And yet, many of you have come to this summer school and you have put yourself into the type of planes my dad used to design, which is just carbon fiber and aluminum. And believe me, these things are not very resistant because they need to be light. You are going to surround yourself with one of the most flammable liquids known to humanity, which is jet fuel. And you are flying around 30,000 feet at 600 miles per hour. And we don't know why this happens. And did any of you thought about this when you were boarding the plane? Oh, you just sit over there. Then the captain says, sit down and relax. And you don't think twice about it. So these guys are engineers. They say the plane flies, it got to Geneva airport, great. The plane crashed and it killed a bunch of people. Well, next plane we need to do it differently. And in fact, the first jet planes during the 1950s, a lot of them crashed. I don't know if you heard about the Caravelle, it kind of crashed all the time because we didn't understand about material fatigue. Now, you are telling me, hey, I want to publish this in Econometrica, I want to prove some stuff, that's fine with me. I'm not against proofs. If I knew how to do the proofs, I'm going to have some proofs today, that's fine. Okay? But what I'm trying just to transmit you the idea is that a lot of the questions you are having, I don't have an answer because the profession at large the profession in computer science doesn't care that much. The answer is, did ChatGPT answer your question properly? Yes or no? Because this is about making money. Okay? The guys from ChatGPT are not trying to punish an Econometrica. The guys in ChatGPT want a house in Santa Barbara. It's a very different goal. Okay? Well, that's what I'm trying. But I keep saving and saving, and the market keeps going up and up, despite all my crazy investments. And anyway, okay. So how are we going to do this in practice? And how are we going to exploit all these ideas in our paper? So we are going to introduce the idea of permutation invariant dynamic programming and the associated idea of permutation invariant economies. So what is this about? Well, until when does the first session go? Okay, well, just let me know and I stop there.
I mean,
No, it's okay. You just stop me, we have 10 minutes and we continue. Okay. So there is a common feature of many, many models with many agents, perhaps even of most models with many agents, which is the following. The policy function of the agent depends on the state variables and the value of the state variables. But it is not different beyond that. That's the symmetry. Okay? The idea is the following. Think about a multi-location model. And imagine that we have, in this multi-location model, every state in the US is one agent. We are going to say how much the representative agent in Texas is going to invest. It's going to depend only on the values of the state variables in Texas and everywhere else. But the word Texas, the label Texas itself does not matter. That means if I take the representative agent from Texas and I gave it the values of the state variables from the representative agent, which one I'm using over there, California, they will behave the same. Okay? There is nothing inherent about being California or being Texas. And the reason why this is a very general view of the world is because most of the things you can think of making California from Texas different, I can think about them as additional state variables. You can tell me, hey, maybe Texas has more population than California. Well, that's just a different value of the state variable population. Maybe the population in Texas has different average wealth, different average income, different productivity. Okay.
So can I ask you something?
Sure.
So we are ignoring like, geolocation, so distance to nearby states. So
And that's going to be the next thing I was going to say. I can also think about that as state variables. Okay, I can say another part of my state variable is the distance between, let's suppose, the geographic center of the state with the other states, and what are the properties of the other states. Okay. Pretty much anything one can think of, any type of heterogeneity can be included as additional state variables. Now, there are things like maybe if they have different utility functions, if one has like a Cara utility function and the other one has a constant relative utility function, I don't know really how to represent that as a state variable. But if the difference is because in Texas there is less risk aversion than in California, that can be just one more state variable. In the same way to what Felix was doing before of adding these parameters as additional states. Okay. Yes.
But adding state variables comes at a price. You always lose symmetry between adding state variables.
No. Because remember, the symmetry is with respect to your behavior with respect to that state variable. Is not the value of the state variable. The symmetry is if I have all the same characteristics that you do, I will do the same that you do. And if you had all the same characteristics that I do, you will do the same thing that I do. That's the symmetry I'm imposing.
Yes, but we might share state variables in common, you and I.
So what?
Don't take into account some other state variables. For example, how tall you are, I might be shorter than you, but if we don't take that into account, we might look like closer alike.
No, but that's again, the point I'm trying to make is your height is another state variable. Okay? Imagine that my consumption function depends. The point I'm trying to make is the following. The consumption function of agent A depends on the income, the wealth, the age, your height, and the consumption, the symmetry assumption I'm imposing is that these two functions are the same if I evaluate it at the same point, which is the standard assumption in any model in economics. Or not in any model, in most models in economics. Okay? So if you are telling me we are different because of something, I will just say that's another state variable. Now, it needs to be a state variable that I can represent as a scalar or a vector. If this was a whole function, if we are different because we have completely different functional forms and those cannot be parameterized, then I don't know how to do that symmetry. I will need to think about it. Okay? But the point here is not that you are taller than me. The point is if I had your height, I will do the same that you do. You see the point? And we do this in economics all the time. We don't write models with 3 agents where, agent 1, when the income is like this, they go in that direction, and agent 2 goes in the other direction. The reason why agent 1 and agent 2 do different things is because they have different incomes or they have different risk aversions, which I can put it over here. But they are the same. That's the whole point I'm trying to say about symmetry. Or let me think about a model of industry dynamics. So, you know, some of you who may come from micro don't feel completely lost. Imagine I'm writing a model, type of a Packes-Erickson model of industry dynamics. Okay? The only thing that I'm saying is that if Toyota has the same productivity and the same models as General Motors, it will make the same investment decisions that General Motors has. And if General Motors has the same productivity and the same kind and the same models that Toyota, General Motors will do the same investment decisions that Toyota has. That's the only assumption I'm making. Yes. Go ahead.
Down to the word max, that, you know,
Yeah.
basically agents are maximizing.
Yeah, they are maximizing. They are not different. So if they have the same inputs, they will make the same decisions. Nothing different on that.
Yeah, what's the limit with unobserved state variables? You include them and you estimate them?
At this moment, I'm not doing any estimation. I'm just talking about how to solve dynamic programming problems. Okay, so I'm not saying I go to the data and I cannot observe something. I'm just saying I'm solving this model. Another different thing is then what can I do to go to the data and estimate the model? But we are not doing that yet. Yes.
To get on the right page for the background, if we had to add 50 state variables in order to make these 50 states look similar, would it still be advantageous in your approach, or is that sort of where it doesn't?
Yeah, I'm going to show you a stuff where we solve this with 10,000 state variables. And we can do with many more, no? Can probably scale this up to millions. Okay. And again, coming back to my point of Packes-Erickson, this is going to be at the very core of what all these models in IO do. All the models in IO basically assume that competitor 1 and competitor 2 are clones of each other. It's just that, you know, one got lucky and got more productive than the other one, but they will behave the same otherwise. Okay. Very good. So what this thing says is that I'm going to be able to take advantage of a very powerful idea, which is going to be perturbation invariance. And that goes to your point before. So what is perturbation invariance? Perturbation invariance is that I don't really need to think about every possible combination of agents. I only need to think about equivalent combinations of agents. So imagine the following situation. Let me go back to the industry dynamics. Maybe the industry dynamics is easier. I'm General Motors, you are Toyota, you are Mercedes. I don't need to worry that Mercedes is having high productivity and Toyota is having low productivity. I only need to worry that one of my competitors has low productivity and the other one has high productivity. That's the only thing I care. Imagine that productivity is the only relevant dimension of heterogeneity. In fact, if you read the original paper by Packes and Erickson, they already take advantage of this. They call it, it's one of these words I can never pronounce, exchangeability. It's just exchangeability. So Ariel and Erickson, they completely understood this at that intuitive level. They just applied in that very particular situation. But if you read Packes and Erickson, you are like, it's over here. Everything I'm going to tell you today is already in Erickson, in Packes-Erickson, which is I only care about the distribution of everyone else. I don't care about their labels. And by the way, this is also what happens in Crusell-Smith. Now, you know, let's go back to some of you who are into macro. In Crusell-Smith, I care about the whole distribution of agents because that's what helps me to forecast prices tomorrow, which determines my decisions today. I don't care that the guy with the high productivity is agent 0.03 to 1, or that the agent with low productivity is 0.398. I only care about how many agents I have with high productivity and how many agents I have with low productivity. So Crusell-Smith has a built-in radical exchangeability. So at the end of the day, at a very fundamental level, Crusell-Smith and Packes-Erickson is the same paper. Because both of them basically say I don't know if Kusalan and Smith and Pakistan Erickson will agree, but you know, to me, from a mathematical perspective, it's the same paper. It's basically saying, I just need to think about everyone else in the economy in terms of this general distribution and not in terms of labels. And then I can actually compute this. So why is this then so important? Because this is going to help us tackle the two components of the course of dimensionality. Remember my mention before about Bellman 1958? So what is the first thing that I'm going to be able to do? That the value and the policy functions are going to belong to the family of perturbation invariant functions. And that means they are going to be able to be represented exactly with an exclamation mark. This is not going to be a freaking approximation. This is going to be an exact representation with a latent dimension. This is nothing more than a particular example of the manifold hypothesis, which very quickly I mentioned before. It's in my lecture notes, and we can talk about that later. Okay? So you're going to be able to accomplish a gigantic dimensionality reduction, and it actually helps us to understand why the Kruskal-Smith method works as the number of agents goes to infinity. Because again, Kruskal-Smith is just going to be in some sense a particular example. But when I introduce some of these ideas momentarily, all this will be very clear. Okay, that's great. We are doing a latent reduction, a dimensionality reduction, because I'm picking the right space to work on. You see the geometry I was telling you? Instead of thinking about the geometry of all the states and all the possible combinations of states, I'm only thinking about the space of possible combinations of states. So I'm working on a much more convenient geometric space. The second point is that I'm going to be able to come up with a fancy concentration of measure. What do I mean by fancy, and why do I mean by concentration of measure? I will define that in a little bit of a second carefully, but a concentration of measure is just a law of large numbers for equilibrium objects. Why is this important? Okay, so think about the law of large numbers that we learn as undergrads. We say, look, I flip a coin, and if I flip a coin sufficient number of times, 50% of the times it's going to be heads, 50% of the times it's going to be tails. The problem of that law of large numbers is that we assume that the sampling process is exogenous. But imagine that I'm not saying I'm going to flip a coin a sufficient large number of times. I say things like I'm going to flip a coin until I get 1,000 tails. Okay? Now the flipping decision is endogenous. So you cannot apply a pure law of large numbers. You need to apply something called a concentration of measure. And the interesting thing about that concentration of measure is that we are going to be able to prove that that concentration of measure is going to be very fast. So the way you want to think about it is that we are going to have a fancy law of large numbers kicking in sufficiently fast for endogenous equilibrium objects. Yes?
Another way to think about your point number one is that there must exist a bijective mapping from a distribution into a low-dimensional space, right? And it must be bijective, right?
Yeah.
Is that proof for that? Or?
No, we are going to show that. In fact, and sorry if I'm jumping a little bit ahead, the heavy lifting in all the proofs of the paper are based on the symmetric group. And the symmetric group, remember, is the group built by all the bijections that you can define over a set. So bijections over here are going to be absolutely key. Okay? But I will come back to that later, because I will assume, I think with reasonable probability, that most of you are not that familiar with group theory. Okay. So why is the concentration of measure going to be so great? Because it's going to basically say, don't worry about computing that conditional expectation that much. It's actually going to be surprisingly easy. If we have a sufficient number of us in the model, yes, there's not going to be the exact aggregation result that gives us the expected value, but we are going to have a sufficient number of people getting positive shocks and negative shocks that the total sum of these idiosyncratic shocks is not going to be very far away from what a law of large numbers will tell us to be. So surprisingly enough, having more agents is not a curse, it's a blessing once you say, I'm going to evaluate the conditional expectations that I need to evaluate with a Monte Carlo. Okay, and again, I'm going to explain all that after the break in more detail. It will be very transparent. What is very important to remember is that even if we do a single draw from a Monte Carlo, the solution that we are going to get is different than setting the shocks to zero. Because you do not want to set the shocks to zero. And the reason for that is because there is a very important idea called the typical set. And the typical set is the set, it's actually going to be an orbit in general, that accumulates the mass that we need to evaluate a distribution. And the typical set of a normal distribution, and in general of other distributions, is not going to be at the mode of the distribution, it's going to be away from the mode. And in fact, the more dimensions we have, the farther away we are going to be from the mode. And this is very important because this is something that economists really get wrong all the time. We don't sample from the typical set. We do things like, oh, let me put the shocks to zero because that's the mode of the distribution. That's absolutely crazy. That's something that should be prescribed forever. You know, there should be a rule of the American Economic Association saying this is not allowed. Okay? In particular, I have 3 minutes and then I stop. Imagine that I have a distribution like this one. The typical set is the part of the distribution you need to evaluate integrals accurately. It's not going to be here. It's going to be a band around here. Let me do it with the stars. This is very important for inference. Because if you, for instance, want to sample from that distribution, you want to stay within this typical set. And that's, by the way, why the metropolis Hastings tends to fail in high dimensions. Because in the metropolis Hastings, the proposal of the density doesn't take account of the typical set, and most of the proposals travel. So even if I'm at the typical set, usually I will travel away from the typical set. That's why, I don't know, if any of you have tried to do a metropolis Hastings 1,000 dimensions, it's really a very different beast. And that's why you want to take advantage of some properties of the gradient of the distribution to stay within the typical set. And that's why you want to do Hamiltonian Monte Carlo. And I have a paper also with some of the same co-authors, not all of them, a big chunk of them, on Hamiltonian Monte Carlo. So that makes that point. And by the way, this is also based on a symmetry result. Okay? But the point is, for this paper, you definitely want to sample from the typical set, and that means you don't want to set up the shocks to zero, even if you are going to draw only once from the standard, from the idiosyncratic shocks. Okay? This means that taking advantage of the permutation invariant representation in latent variables and taking advantage of the fast concentration of measure, we are going to solve today a model with 10,000 state variables. And in principle, if you give me enough memory, we could do this for millions of state variables. Okay? And I have already working up some work, follow-up work that does that. So how are we going to do this? Well, let's take a 10 minutes break because we already went over a fair amount of material. We can come back to that, and then we can think more about heterogeneous eliminators.